So I'm going to talk about nanoscale machinery that we built from DNA and some sort of suggestions on how we can make it perform better. And this will overlap a little bit with Andrew's talk, but I'm sure that repetition is just good. So I'm just going to start by showing a slide to those in the audience who don't really work on DNA nanotechnology to show that over the last decade there's been a ton of impressive mechanisms made from DNA. And this is just a few of them, so they can be sort of linear actuator, rotors, and other things, and they can also be controlled by things like chemical environment and even electric and magnetic fields. So we're sort of building on a rich vein of work. And what we decided to work on is try to build a 2D molecular printer from DNA. So just working from this kind of simple sketch of a 2D gantry with a central sleeve that's capable of moving on one rail axis, and then that rail axis in its turn is able to move in the second dimension along a base axis. And we chose to implement it in DNA origami, which is what we work with. And in order to make it big enough, we had to work with 3 separate DNA origami structures, creating sort of central blue canvas, a green frame structure, and then a smaller yellow sleeve that wraps around the rail arm. And we were able to not on the first try, but after a while we were able to assemble these devices and be able to see them in different types of electron microscopy. So the way we chose to do positioning is via diffusion. So in this design, the sleeve wraps a central rail arm, and it's topologically locked to that rail arm, and the rail arm in its sense is locked to the base beams via flexible linkers, which means that when everything is released, it's free to diffuse around. And what we did is we decorated the rail arm and the base beams with unique address strands that are shown in red here. And by working with the structures immobilized in flow cell, we could add unique address strands that brought the sleeve to a specific position on the rail arm, and in turn the rail arm to a specific position on the base beams to create 2-dimensional motion. And kind of importantly, we can use toe-hole mediated strand displacement to reverse this process, to release the sleeve again, to go back to 0 and reposition it. And we've been exploring. We've been exploring a few different positions, putting it into and studying with DNA paint. And what we do to study this is we take DNA paint images of hundreds of devices and we just average it. We line the data on averages and see that we can drive it in the position we want. And we're also able to do this reversibly to reposition the device. And then moving on, we of course thought about how can we turn this sleeve into right head? How can we get it to perform some type of chemistry at the bottom? And we chose to go all DNA because that's what we work with. So we added an array of pixels on the canvas that are initially blocked double-stranded duplexes, but when interacting with so they can be the blocker on the pixels can be removed by toe-hole mediated strand displacement again, and this reaction should be very slow in the absence of a extra catalyst strand that we place on the bottom of the rail arm to get a very high local concentration to facilitate this incorporation of the ink and pattern the canvas below the right head. So I think like a key question that we're wondering and people weren't wondering when seeing this is what's the precision of positioning, because DNA is a rather flexible material, and I can just tell you it is quite difficult to estimate experimentally because things are pretty small and it's quite slow to work on. So I mean what I think is that we can try to answer this question by simulation. So, as we talked several times today, I think OxDNA can offer a rapid alternative to experiment and give kind of an estimation of the precision, especially of the slider to the right. You can see that it's fluctuating over the surface in a sort of a 10 nanometer diameter, not completely isotropically. And what I think is kind of important is that it's very painful to improve a system like this experimentally because, as I said, it's quite difficult to even measure the precision experimentally. So if we believe that simulation offers a rapid alternative, then we should probably use simulation to improve this type of device. So I'm going to move on to something that I worked on a few years back. So I was working with wireframe DNA origami structures, and we had sort of hoped that they would be very rigid because that's what you see in lattice work on the microscopic scale. But it turned out they were quite soft. I mean, this is a little bit of an exaggerated example of how soft they can be. But again, we had the same issue that we had this kind of soft structure, and we can probably use oxygenate to estimate the performance of this device, especially specifically the flexibility of the structure. And it's not easy for me to say how I should change the structure to improve the performance. So we tried to implement this in an iterative way, where we start from a sort of mother structure and then mutate it to create a family of mutate structures, then simulate all of them in oxyDNA and select a winner to use as the spawn for the next generation. And that's not always obvious which structure to choose as the winner. And we used a few different approaches for this. And I'm just going to talk about this one. So we initially worked with hollow structures, and we decided to reinforce them by adding these sort of diagonal struts that run straight through the structure. And to look at the performance of a structure like this, actually you can just look at the sort of end-to-end fluctuation of the structure, and that's giving you a good proxy for the rigidity of the structure. And looking in oxygenate, the end-to-end fluctuation is pretty big. So the way we iterated the structures is we allowed the internal support to walk inside the structure. So we just disconnected one arm and then just reconnected it somewhere else randomly to create a family of mutant structures, and then simulate all of them and selected one of them for the next generation. So what you can see here is that in this case it's just a plot of the iterative progression, and there's just in around 20 or so iterations, you get a drastic increase in this sort of performance metric. And so every dot here represents 8 oxygenate simulations. So what I think is important to stress is that even about 5 years ago, we could simulate hundreds of structures on that times hardware. So I think this is a very feasible approach to put into any DNA nanotechnology system. And sort of the selected best one here is quite interesting. You see the position of the internal supports are actually not in what you might expect. But when you look at the orange curve showing the end-to-end fluctuation, it's much smaller than compared to the original blue one. So it is something that's approachable. So I'll just end with some conclusions and outlook. So I think that DNA offers a good route to molecular machinery, but there's still a lot of work to be done to allow the precisioning and to increase the precision. And of course, I think we should try to do more interesting chemistry and patterning. And I just want to say that I think today it's comfortably feasible to simulate thousands of DNA nanostructures in simulation tools. And I think it's very worthwhile and not very expensive. So I think we could be much more clever than our initial naive approach about how to mutate them, how to evaluate them, and how to select the progression. I think it can be really useful for any type of DNA nanostructure. And with that, I want to thank all the people in the Turbofield lab and our collaborators in William Shee's lab and their funding. Thank you.
Really interesting talk. I'm fascinated by your second to last slide where you showed that the, one more back, yeah, it looks like it's sort of a random assortment of those red struts, makes it much more rigid. Do you have any insights into why that is from a fundamental perspective?
No, not really, but I mean, I think there is kind of similar examples at the macro scale in this kind of inverse design problems, right? That these kind of naturally occurring shapes. I think it's very difficult to anticipate exactly what controls sort of the end-to-end rigidity in this very like coupled system. So, and of course it might be interesting just looking at it now to do something engineered comparisons just by, but this is the best that we came up with. Yeah, sorry.
Great talk, really interesting. 3 questions. First of all, like, can you comment on what's the scale of your simulation? For example, like how long it take, for how many mutations, and second of all, like, how sensitive is your system to mutations, like the structure, like how many mutations you can do without like actually changing massive structures. And lastly, have you ever done experimental characterization of your mutations on the structures, and then how much do they correlate, do you think?
Okay. So these sort of simulations take around a day on a GPU, I guess, would be an answer. So if you have 8 GPUs, you could do 8 per day or something like that. Second question was, what was the second question?
The mutation, like how much tolerance you can do for the structure. Let's say you mutate on some range of the sequences, and then it doesn't really actually care. It doesn't really change.
Oh yeah. So, well, I mean, a lot of mutations are not beneficial, but maybe that's not. So they are thrown out, and of course, every dot that we show here is just the best value of, I think, 8 in this case, and sometimes 16. And these are relatively large mutations, and so the bulk of this work was more on just these sort of single insertions and deletions. And then a lot of mutations had very small effect, or detrimental effect, of course, to the performance. And then experimentally, so this is the most interesting system, and unfortunately, it doesn't assemble very well, either of them. So unfortunately, for...
I'll just spell it out. So one idea about why this structure is good is that these odd struts might be damping vibrational modes, so it's not able to vibrate in a certain number of modes.
Yes, yeah, thank you. I can also just speak up.
Okay. It seemed, based on your explanation, it seems like you're using a genetic search algorithm for the by changing the seed at each step, but when you randomly sample the different mutations in each step, did you ever consider, or did you implement any kind of like stochastic process, for example, like a Metropolis Monte Carlo method or anything similar to for the random sampling?
Yeah, so that's true. So in this case, it is based on simulated annealing. So we tried gradient descent and had issues with that. We sort of got stuck very quickly, and then moving to gradient descent, to simulated annealing greatly helped. And I think there's a lot of interesting other approaches you can do, like even genetic, like combination of things, but we haven't gone yet to those.
Okay, thank you.
Thank you.